So first of all, we'll see what is FFT. A fast Fourier transform is an algorithm that computes the DFT of sequence or its inverse. So first Fourier analysis converts its signal from its original domain to a representation in the frequency domain or vice versa. Which of the following is our applications of FFT? So it covers FFT's frequency domain filtering and applications to video and audio processing, as fields like communication, speech and image processing and related areas are rapidly developing. The FFT as one of the essential part in digital signal processing has been widely used, that we all know. Okay, let's start the project. So in this tutorial we will explain how to use the FFT core of Zynq processor given in Vivado software. So there is my earlier project which already I have described in my channel. I'll give you the description of the link of video tutorial so that you can access it. This is the basically DDS compiler where we are going to generate the sine wave signals, and through this signal we'll do the FFT with the FFT code. So we are simply adding the FFT code here. So I'm not going to describe again this portion, this DS compiler, how we are generating the sine wave signal. It is already given in my earlier tutorial, so you can access that tutorial to gain knowledge about this. So here we'll add FFT core, FFT. So this is the FFT transformer. Let's go here. Now we'll open it, the parameters of this. Okay, now you see here's the block diagram, as the implementation details. This Redis 4 burst IO it is using, and 9 number of display slices has been used. Block RAM 7. This data port. We'll configure it. Now number of channels 1, as we are only using one input channel. Transform length 1024. You can use according to your requirement. We are using 1024. Target clock frequency we are giving 100 megahertz. Target data throughput also we will use 100 megahertz. We'll use this data throughput rate is 100 megahertz. Just left it as it is, automatically select, let them choose it. Now go to implementation. Now implementation section, data format we are using fixed point. Scaling option we will use scale, and rounding mode, two options, conversion, rounding and truncation. We will be using truncation. Scaling point we will use scaled. We'll don't need scale, we'll use unscaled. Here the throttle scheme we will use non-real time. In the detail scheme, these are the things but we just need it. Simply click OK. Now we'll add another ILA. We'll just configure it. We need native probe as well. 63-bit code, 64. Okay, now it's we are just this is the port I'm connecting. Access button, access, connecting this. This is the T ready pin. We'll have to connect it to this thing. The T valid data, we'll have to connect it. Configuration T ready, we'll connect it. We don't need this. There's the configuration. There's the M. This will make it external. We need this. We'll be seeing this the thing. Now it will be connected to here so that we can view the sine wave signal. So that's my design. This is here the layout. That's the complete design. So now okay, validate it. Okay, validation has been successfully completed. Now we'll simply what we'll do, we'll generate the VHDL wrapper file. This will just simply run behavioral simulation. It will take some time as it is processing the whole data for simulation. Okay, now the waveform panel has come. Now we'll simply delete these things. We'll add here. We'll add the things. First of all, our design ILA. This is the sine wave signal. Will be seeing through this, so simply add to wave. And then like this, we'll go to this, and this is the T user data. We need this. They show us the data, the clock, and access T valid, T ready. So access T ready, this thing. We have to add T valid, we have to add, and one more thing, we'll have to add this also. Okay, so these are the things. Now we'll have to make it force clock, give 1, 0 trailing edge. As we are using 100 megahertz signal, so we'll just remove 1 0. It has 10 nanoseconds, that means 100 megahertz signal. Clock, so T valid will give a force constant, that is 1. Okay, so these things probe will make waveform style analog, and radix will make sine magnitude, data will make it analog, will make it analog. Now simply run it. Okay, we'll add the DDS compiler to output, that is T data, so simply add it, and full style make it analog, make it radix sine magnitude. This is the signal, so again rerun it. So here we can see that. Let's pause it, place a marker, again place a marker. So see, the time difference is 36 microsecond and 35 minutes, that is 1 microsecond. Period is 1 microsecond, that means the generated output signal is 1 megahertz signal. So I can run it. So after some time, this MXS T user data, it will show us it will show us some signal, so that we can calculate our frequency. Okay, see, here it is going. This thing is increasing. Where it will be stopped, that will be our data. It is continuously increasing. Yeah, that's the point. So here you can see that's the point. So that is 4085. So at 4085, I'll show the calculation. So let me show the calculation here. This my assembly means is 100 megahertz. 3, 4, 5, 6, 7, 8. It has become to 44. Now we'll my input signal frequency is 1 megahertz. So 1, 2, 3, 4, 5, 6 divided by 244, that is 4098. So it is approximately, our thing has come 4085. That is the index. So it will show that my input frequency is 1 megahertz signal. That is the thing. That's how you can calculate the FFT signal. That's all. Thank you so much. If you like my videos, if you like my tutorials, please subscribe my channel. Thank you so much.